Good day everyone. My name is Wim Bastiaanse and I'm the CEO of IrriWatch, and I'm also a professor at Delft University. Today I would like to tell you a bit more about the physics of the crops and the soil, and I would like to relate that to thermal remote sensing, because with this kind of images we can look into the soil, and I want to tell you much more on how this technology works. Because it regulates the conditions of our climate and vegetation, the soil is very important to us. Yet we hardly understand what happens below our feet. Water infiltrates into the soil and it's stored and taken up by roots again. Besides water, the soil also stores carbon, nitrogen, nutrients and minerals. But we cannot look into the soil. So we don't know what happens in the underground. There is a very distinct vertical and horizontal variability, which is related to the sedimentation process. So one thing is very sure, the soil is heterogeneous. Yet, every irrigation lecturer at the university will tell you that you should know your soil moisture before you irrigate. And you should know the water holding capacity of that soil. So, this contradiction between the limited knowledge we have of the soil properties and soil moisture at the one hand, on the other hand, the practical need to irrigate is a dilemma that we have to break through. And everybody's talking about making irrigation systems more efficient and to increase our water productivity, but in the end it's all about soil moisture management. So we really need a good measurement system of soil moisture. If we can reduce the total amount of applied water to irrigation systems, we can keep water into the reservoirs, and also we can keep water into the aquifers. And that is what we want, to have less water being withdrawn and more water to be remaining into the natural habitats of this water. In this short lecture I will explain you how the crop can be used as an indicator of the soil moisture conditions. In fact, if we understand the crop better, we can learn from it, because the crops tell us indirectly what is happening in the underground. And one challenge is to measure the crop every day, because the soil moistures are dynamic. And a second challenge is to include the spatial variability. Now the good thing is that satellites measure the leaf temperature every day, and they can look from 700 kilometer altitude into the soil. And they can also measure complete landscapes. So they measure all the differences in the catchment. So what I will do in the first part of this lecture, I will tell you more about soil moisture. I will deal with a number of very practical questions that every irrigation engineer has to deal with. And then in the second part of my lecture I will tell you much more about remote sensing, how this works, and with a special focus on thermal infrared, which means the temperature of the leaves. So let me now start with the first part of this lecture, which is related to irrigation and soil moisture. So the first question is always, why soil moisture is so important? Why is it so relevant? Well, they withdraw water from the soil through the roots. And this depth from where the water is taken is not always known. It changes because the roots are dynamic. The depth of the root depends on the type of soil, the organic matter, but for instance whether you have a hard pan or a bee horizon, or perhaps simple the impact of a mole, that's making his own pores in between the soil particles. But one thing is sure, the soil roots also are dynamic. So the roots go deeper when the crops further develop, because the crops need more water when they go through the various crop growing stages. So the roots also have to grow. It's very common knowledge that the crops need carbon for growth, and this carbon is coming into the crop from the atmosphere via the stomates. So the stomates are these very little openings in the leaves that are used to intake the carbon from the atmosphere. The water has to come from the roots, and together they will create dry matter production. But this process of photosynthesis requires also all kinds of nutrients to be part of the process, and these nutrients have to come from the solution into the soil. Roots take this water up and bring it into the crop where it is needed. But the crop has its own water balance. So the uptake of water from the roots should be in balance with the amount of water vapor leaving through the stomates into the atmosphere. Otherwise the crop will become one big bowl of water. So this inflow from the bottom of the crop and the vaporization into the atmosphere from the leaves have to be understood, these processes. Now, this vaporization of water consumes energy. And because of that, the leaf of the crop will be cooling down. And that is exactly the part we can measure. So we can measure the leaf temperature and then indirectly the conditions of the stomate. So that is, say, why soil moisture is needed. Soil moisture is needed to create dry matter production, but also soil moisture is needed as a sap flow to bring the required nutrients into the right places of the plant. So how do we know then? How do we know the current level of soil moisture? Well, we can measure it by field equipment. We can bury sensors and probes and tensiometers in the subsoil. But this depth is always very dependent on the root presence, and we don't know that very well. And moreover, the roots, as I mentioned before, are dynamic. So roots also grow, they get bigger, and it's not so easy to measure exactly the effective, let's say the average moisture within the root zone. So there is a layered profile of soil moisture, and there's a lot of spatial variability. Soil properties, as I mentioned, are very heterogeneous, and even within a distance of a few meters, the soil moisture can be significantly different. The other aspect of the measuring soil moisture is its dynamics. So the dynamics are also great because the weather changes, but also the percolation towards deeper layers. Moisture is variable in space and in time. Yet we have to know it. And the best way to do it is to measure it from remote sensing, and I will explain you in a minute how we do that. Another thing that should get your attention is the unit of soil moisture, and I see all kinds of different people using different units. They say soil moisture is something like so many percentage. Okay, but is this percentage on a volume basis or on a weight basis? This is the first mistake often made. The second point and mistake is that the soil moisture percentage is also related to a reference. So what is this reference? Is it full saturation, or is it maybe the maximum soil moisture ever measured in a time series? Actually, this reference, this point of reference of soil moisture is hardly provided, and this makes it very difficult to interpret soil moisture. So my advice to you is when you talk about soil moisture, express it in a cubic centimeter of water per cubic centimeter of soil, and then you have like a volumetric fraction, and then it's clear what you talk about. It's also important for the water balance, because the water balance is also in volumes and in millimeters. So once we have volumetric soil water content, it's much easier to use in our calculations. So then one of the next questions is, okay, if I can measure my soil moisture, when should I irrigate again? And to understand that question better, it's good to think about the cohesion and adhesion into the soil pore. The adhesion is between the water droplets and the wall of the pores. The soil moisture is bounded towards the soil matrix with a certain amount of energy, which we refer to as soil water potential. In fact, it's a suction, so the amount of moisture is sucked towards the soil pore. So it's negative. People call it a negative energy because of the suction forces. You can say in general that smaller pores, such as for instance clay, have a stronger adhesion, so they bind the water with more force than a sandy soil, because a sandy soil has larger pores and all these adhesive forces are simply less developed. So in other words, a plant has to do much more efforts to take a drop of water from a clay soil than a drop of water from a sandy soil. Another key aspect is that when the soil gets drier, the remaining water is bounded with more forces. So the drier the soil gets, the more difficult it becomes for the plant to withdraw that water out from the soil matrix. And that is something that we know from our lectures as the soil water holding capacity. The soil has always a certain capacity to hold the water, and it is between the field capacity of the soil, which is a suction of minus 100 centimeter or 0.1 bar at the one hand when it's wet, but at the dry end we have the wilting point, which is usually 16,000 centimeter of suction or a column of 16 meter of water. This kind of, let's say, capacity, reservoir capacity of the soil is very important for the scheduling. Now the roots have to undergo a competition with the soil. The soil wants to hold the water and the roots need the water. So the one with the highest suction wins. But this is a soil crop property. So crops like rice or strawberries, they are not good in developing strong suction forces. So it means that soil has to remain wet for them in order to withdraw water into the crop as subflow. Whereas, for instance, crops like barley and avocado, they are at the other end of the spectrum. They have the capacity to withdraw much more water, and even when the water is bounded with more forces, they are still able to get the minimum amount of water they need. So it means that the scheduling of irrigation is on the one hand related to the water holding capacity of the soil, but it's also related to the type of crop. And in fact it's even more complicated, because this process is also impacted by the atmospheric conditions. Let me give you an example that if you have a hot day with a lot of solar radiation, you may have a transpiration rate of the crop of 5 millimeter. But if this crop is evaporating with 5 millimeter, and if the soil, if the roots in the soil are not having the capacity to withdraw 5 millimeter, the plant starts to wilt. So there is also a mechanism included into this crop physics that it prevents the plant from wilting. So it is again showing the dynamics of the regulation between water in the soil and then water in the plant, but also water into the atmosphere. usually the stomates, they respond to this sap flow because if there is the water is not easily available, then the sap flow will be reduced and the stomates respond. Otherwise, there will be going more water out of the crop than into the crop. And this is exactly where the opportunities are for our measurement system, because we can measure the stomatal activity from the temperature, and through that mechanism we can understand also what happens in the root zone. So the only thing an irrigator has to do, it has to take care that the water into the soil is having a certain potential that is less than the critical one at which a certain crop gets stress. When the crop gets stress, the roots are not able to pull out this water from the soil matrix. Stomates close, and if the stomates close or they partially close, the carbon intake will be much lower, and a lower carbon intake is translated into less dry matter production. So an irrigator should always take care the moisture, or in fact, if we want to say it more scientifically, an irrigator should take care that the soil water potential in the root zone is always above a certain critical value, so that there is no stress on the crop and the carbon assimilation is reaching a maximum rate. So that's good, because that affects the moment of irrigation scheduling. But then the next question is, okay, how much water can I apply? Is it 2 millimeter or 4 millimeter? Or how much water is really needed? Now to answer this question, we have to go back into the mechanisms of the soil moisture, and the transpiration basically is a sink of water, and because the water is taken out from the roots. There is also percolation that goes to the underground, and there is evaporation from the soil surface. But after a couple of days, percolation is very little. Percolation mainly occurs if the soil is at field capacity or above, which occurs if you over-irrigate, like with flood irrigation. Flood irrigation is almost unavoidable to have percolation losses. If you have a good drip system, you should manage it in a way that the moisture is always below field capacity, otherwise you get percolation. So if you do well, you should irrigate in a way that you meet the amount of water that is going as a sink from the soil into the crop. And so you have to know much more about this transpiration flux, which more popularly is called sap flow. So this brings me to calculations of crop evapotranspiration, and I like to call that crop ET. ET is evapotranspiration. Most irrigation countries, they have a system where the crop ET is estimated from a reference ET, which is a reference crop. Often the FAO reference crop is taken. It's 12 centimeter tall and has an albedo of 23%. And then once you have that ET of a reference crop, you have to multiply that with a crop coefficient in order to get the ET of a certain crop. This is a classical approach. It has been used for many years, but there are also a few limitations, because it's based on experimental measurements where everything is 100% pristine. There is no stress. Everything is perfect. It's also based on the fact that you need good weather stations, and if these weather stations are not in a proper place, then you get an overestimation. So reference ET values from national weather departments or national weather services can be misleading, because the stations they used to measure ET reference can be on non-representative places, such as airports or other very secure areas. In fact, the weather stations that we use for crop ET calculation should be on the farm. And then not at the farmhouse, but inside the field, in the middle of the field. That is much better. So it's very good that FAO has developed these procedures since the early 70s. This is excellent work, but it's not perfect. And I think after 50 years it's time for something new. In fact, if you look at the current irrigation scheduling, how it really goes, and it's more like this, that in most of the cases it's still intuition. Whether you go to Europe, or you go to Middle East, or you go to US, most farmers, they just irrigate on the basis of intuition. It's much better to take the ETO, the ET reference, and to take a crop coefficient. But again, you know, this is also not perfect, and this crop coefficient can be obsolete. It can be measured some 25 years ago or longer ago, maybe even in a different country. So think about if you are in India and you need a crop coefficient, and this crop coefficient is just measured in Australia 25 years ago. You know, that's not the perfect way. So keep in mind that these kind of methodologies can really be leading to errors of 20 to 40%. This is very important in the current situation where the society is looking at irrigation sector, and the irrigation sector has to improve efficiency, and has to improve water productivity. So we should also become more accurate on our calculation of water requirements and irrigation scheduling. So that's why IrriWatch is coming up with a new solution, and that is based on daily satellite measurements. We use about 6 different satellites that we use in combination to compute a number of key factors. The core engine of IrriWatch is based on an energy balance model. Some of you may know my name from the international literature, where I have published the CBAL model, which stands for the Surface Energy Balance Model for Land, some 25 years ago. And this CBAL model is now applied in more than 45 irrigation countries. So I have been looking back to the CBAL over the last 2 years, and really made a 4th generation version of this model, so that we can look a bit better on crop ET and also on soil moisture. So let me tell you in the remaining 5 minutes a bit how CBAL works. So it's a key energy balance, and the energy balance is based on the absorption of energy from the sun, which is shortwave radiation, but also from the Earth and atmosphere, which is longwave radiation. The energy balance is composed of a net radiation. Net radiation is, let's say, the engine. It's the amount of total energy available, and it drives the processes such as ET. But not all this energy can go to ET. So part of that energy is going to soil heat, flux, which is related to the heating of the soil, and another part is related to the heating of the atmosphere, which is also called sensible heat flux. CBAL computes all these fluxes automatically by using temperatures of the satellite, but also by measuring other properties such as the surface albedo, the vegetation cover, the leaf area index, and also we look at cloud cover, because the incoming radiation from sun is very dependent on cloud. Now, when we see that the pixel is very hot, then we know for sure that most of this net radiation has gone to heating of soil and heating of atmosphere. And that means the temperature has risen, but there is very little energy gone to ET. If we look to a very cold pixel, it's the opposite. then most of this net energy goes to ET. And because of that, the pixel is cold. It's referred to as evaporative cooling. So by measuring temperature, we can say more about evaporative cooling, and that's how we can get the actual ET. Now, this is very handy, because ET otherwise is very complicated to measure. Field equipment are very complicated. Weather stations only measure reference ET, not actual ET. And also the modeling is very complex, because what is the soil properties, what is the role of diseases, how well is the crop developing, and so on. But if we can derive the ET as the residual from the energy balance, we don't have all that problems. We don't need to know the type of soil and the age of the crop or the variety of the crop and so on. So that is very big step forward. In fact, we can say, look, since we got the ET in an independent way from an energy balance, we can in fact also look at, well, can we not use that information to inversely model, so looking backward on what will be the associated soil water potentials and soil moisture. And this is what we do by checking the transpiration, and we look at the stomate. So the stomate here is the key element. It's in summary, we measure thermal, we measure leaf temperature, we have a number of additional crop parameters like leaf area index, albedo, and we put it all into a complex model to inversely solve the stomatal resistance. Now, the stomate is micro scale thing. So our big simplification is that instead of modeling the stomate at the micron level, we model it at the 10-meter level. So this is what Professor Monteith called the big leaf. So the 10-meter pixel we consider as one big leaf. So we get a total stomatal resistance at 10 meters. But by using recurrent satellite data, we get it every day. So the stomate is essential. We get the temperature. The temperature is also a physical factor. The law of Planck is fundamental here, because every crop that is having a different temperature will have a different emission of thermal infrared radiation, and satellites have a thermal infrared camera, and so we can really then get into the leaf temperature values. So that's already a lot, and the last part of my lecture I would like to tell you a bit more on the other parameters that we get from satellites. And for this you have to understand that most satellites measure in what we call the visible and near infrared part of the solar spectrum. So solar is electromagnetic radiation, and we look at the reflectance of that radiation in smaller parts. We look at spectra. And the human eye can only see visible light. So we see blue and green and red, and that's it. What is interesting is that this visible light is the main source for photosynthesis. So photosynthesis is happening because of the chlorophyll in the leaves, and this chlorophyll is like the human eye. They only can catch visible light. And it means that a lot of visible light is absorbed by this chlorophyll for the photosynthesis, and very little is reflected. And that's a pity, because the human eye cannot see so much about the crop and the crop health. If we go to infrared, in fact, there is no photosynthesis in infrared, so much more solar radiation is reflected, and because of that you get much stronger signals. So if we would have had infrared eyes, we could have seen much better what's going on with crops, with the health, with the photosynthesis and crop growth and so on. So we can say also differently, by using satellites we can measure near infrared and shortwave infrared reflectance, and that is providing a lot of additional information that otherwise we will not be able to see. So what IrriWatch is doing, IrriWatch is integrating all these different pieces of information together. So we look at the temperatures, we look at reflectances, we look at albedos. Yes, we also look at NDVI, but we really look at many more indices so that we have a more comprehensive understanding of what happens in the crop. So to summarize my lecture, moisture is very dynamic. We need to know moisture in the root zone. It's very complex to measure that from field devices, although we have to. We always need field instruments to check. But field devices and field instruments cannot give us the full picture. It always has to go together with satellite measurements, and the power of the thermal data is very useful to look at the real biophysical processes of root water uptake, sap flow, transpiration from the stomates, and so on. Now I realize this is not a full picture, it's a very complex process, but I hope nevertheless that this helps you to get a better appreciation of these processes, and that a combination of the proper physics and a proper measurement system can really give us a much deeper understanding of the dynamics of irrigation. Thank you for watching, and you can have more information on the IrriWatch website. Thank you.